Hello friends, IBM is here with the part 3 of work, energy and power. I'm trying my level best to accomplish these episodes of work, energy and power before exams next week, and I'm very sure I'll accomplish them as soon as possible. So we are going to part 3. We stopped on part 2, and I think in part 2 we stopped on around page 30. I think we stopped on page 30. Okay, I think we stopped here on page 30 and we are going to page 31. Okay, without wasting time, let's start with page 31. We're on page 31. I'm using green today. An electrical generator is started at time t equals to 0. The total electrical energy generated during the first 5 seconds is shown in the figure. What is the maximum electrical power generated at any instant during these first 5 seconds? Maximum electrical power generated. Remember, power is equal to energy, or the change in energy over time, or the energy over energy per unit time, or the work done per unit time. So we are looking for the maximum. So the point where we expect maximum power is the point where the change in energy is smaller, and yet the change in energy is smaller, or the change in energy is bigger, but the change in time is going to be smaller. That is when we shall have maximum output power. And when you look at this graph, you notice that the maximum change in energy is between 10 and 40. So the power is going to be 40 minus 10 divided by the time, which is 40 is correspond to 3 seconds and 10 is correspond to 2 seconds. So this is 3 minus 1. And this gives us, that is 30 divided by 2, which is, this is 30 divided by, so this is 3 minus 2, not 3 minus 1. So that is going to be 30 divided by 1, which makes it 30 watts. So the answer here is going to be C. In normal driving conditions, an electric car has a range of 150 kilometers. This uses all of the 200 megajoules of energy stored in its batteries. With the batteries initially fully charged, the car is driven 100 kilometers in normal driving conditions. 100 kilometers in normal driving conditions. That is, with the battery initially fully charged, the car is driven 100 kilometers in normal driving conditions. We can find the energy here. It has a range of 150 kilometers. This uses all the 200 megajoules. So if 150 kilometers uses all the 200 megajoules, then what amount of energy is used for 100 kilometers? So that one is very easy. It means the energy used for 100 kilometers is going to simply be 100 kilometers divided by 150 kilometers, then times 200. That is the energy used for 100 kilometers. So this is going to be, I'll just cross out these zeros, or I have to leave 1 0 here. So this will be 200 divided by 15, which I think would be, I think this is 4, no, it is 2000 divided by 15, because I've left 1 0 here. And I think this becomes, by 5, this will be 400. And by 5, this will be 3 megajoules. So that is the energy used for 100 kilometers. So the question is, what is the minimum time required to recharge the batteries? So the power in this case is equal to current times V. That is the power used for recharging. And the power is going to be 13, then times V, which is 230. That is the power. So that means the energy is equal to power times time. And remember, the energy used is 400 over 3 megajoules. So I will simply say that 400 divided by 3 mega, that is times 10 power 6, is going to be the power, which is 13 times 230, then times t. I'll just press my calculator. So I have 400 exponent 6 divided by 3, then divide by 13 times 230. So this is giving us time in seconds as 44,593. So the time in seconds is 44,593. 44,593 seconds. We just change it into hours. So this time into hours, we divide by, change this time into hours, we shall divide this time by 1 hour, that is 1 hour is 3,600 seconds. So this will be 44593 divided by 3,600. So when I check this with my calculator, this is giving me 12.4 hours. So this is 12.4 hours. So it means our answer is going to be B. Water from a reservoir is fed to the turbine of a hydroelectric system at a rate of 10 kilograms per second. So this is mass per unit time. The reservoir is 280 meters above the level of the turbine. The electrical output from the generator driven by the turbine is a current of 2.05 amperes at a potential difference of 5,800 volts. So that is the output. Output voltage, output current. What is the efficiency of the system? So we have already seen that efficiency is the useful power output divided by the power input times 100. So this is going to be the power output. Of course, power will be I times V. So the power output here will be I times V. Then the power input, this is the mass. The hydro system, the turbine of a hydro system at a rate of 510 kilograms per second. Water is fed at that rate. So this is going to give us the input energy. So the input power is going to be equal to the energy divided by T, which energy is going to now to be mg times H divided by T, but we have m over T. So this is going to be mass per unit time, then times G times H, the height to which the water is raised. So by simple substitution, this is going to be 205 times 5,800. Then we divide this by mass per unit time, which is 510, times G, which is 9.81, then times the height, which is 280. So this gives us 205 times 5,800. Then we divide this by 510 times 9.81 times 280. So when I multiply this by 100, it is giving me 85%. So times 100%, it is going to be 85%, which means the answer will be D. A force of 100 newtons is needed to lift the hook of a crane at a constant velocity. The crane is then used to lift a load of mass 1,000 kilograms at a constant velocity of 0.5 meters per second. What is the power needed to lift the hook and the load? What is the power needed to lift the hook and the load? So since we know that power is equal to force times velocity, all we need is the total force required here, because the force, this is the force needed to lift the hook alone, but there is also force needed to overcome the weight. So the total force here, F, is going to be equal to 1,000 newtons for the hook plus the weight of the load, which is going to be mg. So this is going to be 1,000 times g, which is 9.81. So this is giving us the total force. Therefore, the power is going to simply be equal to 1,000 plus 1,000 times 9.81, that is the total force. Then the system will move at a velocity of 0.5, so I'll simply say times 0.5. So this will give us 1,000 plus 1,000 times 9.81, that is total force, times 0.5, which is giving us 5405. So this is 5405, which is approximately 5.4 kilowatts. So the answer will be B. A rocket is fired upwards. It is fired upwards. It is fired upwards. As it accelerates upwards after leaving the launch pad, which forms of energy are changing? Of course, it is moving upwards. it accelerates. As it accelerates, that means the velocity is increasing when it is going upwards, so the kinetic energy is changing. It is going upwards, so it is gaining height. Gravitational potential energy must be changing. So if it is fired, then fuel is going to be burnt, and by Newton's third law, as the exhaust gases are propelled downwards, the rocket is going to be propelled forward. So there must be chemical energy. So the chemical energy will change as more fuel is burnt. The gravitational potential energy and the kinetic energy will also change. So all those three will change. So the answer is going to be A. I think that is a repeated question. A mass M is on top of a platform that is supported by gas in a cylinder of cross-sectional area A as shown. The platform has negligible mass and can move freely up and down. The gas is heated and expands so that the mass is raised through a height h. Atmospheric pressure is P. What is the ratio gain in gravitational potential energy of the mass over work done by the gas? So first of all, the work done by the gas is going to be work done against atmospheric pressure, which is going to be pressure times change in the volume. And the change in volume is going to be equal to the cross-sectional area times the value of h. That is going to be the work done. So that is the work done. And then that is the work done in moving the mass m upwards, or I mean the work done by the gas onto the mass m. Then the gain in gravitational potential energy, of course, gain in the potential energy is going to be the work done to overcome that weight. So the work done to overcome that weight is going to be equal to mg times h. That's the work done to overcome the weight of the mass m. So we simply want the ratio. The ratio. So what is the ratio? Gain in gravitational potential energy. Let me call this one work W1. This one is work done against atmosphere. The work done against the atmosphere. This is against atmosphere. Work done against atmosphere. Okay, that is the work done against atmosphere, which is going to be pressure area times h. Then W2 is the work done, which is going to this one I'll call W2, which is going to be the work done to overcome the weight. Or let me just say, to overcome the weight, we need to do this work. So to overcome the weight, W2 is the work done to overcome the weight. So this is the work done against the atmosphere, and this is the work done to overcome the weight. That means the net work done is going to be the sum. The net work done is going to be the sum, which is going to be W1 plus W2, that is pressure, area times H, plus mg times H. For the first part, there was a change in volume here. That's why I said pressure times change in volume. Then we are trying to overcome the mass m, to overcome the weight of the mass m. That's why we have mgh. So that is the total net work done. So we now want the ratio. Gain in potential energy of the mass, which is simply mgh, divided by the work done by the gas. The total work done by the gas is the work done against the atmosphere plus the work done to overcome the weight of the mass. So the ratio is simply going to be mgh divided by pa plus mg into h, and of course h cancels out. So that means our answer is automatically going to be B. The force resisting the motion of a car is proportional to the square of the car's speed. So force is directly proportional to the square of the car's speed. The magnitude of the force at a speed of 20 meters per second is 800. So force, when the force is 800, so this will be equal to a constant times the speed, which has been given as 20 but squared. I'm just using this equation here. What useful output power is required for the car's engine to maintain a steady speed of 40 meters per second? So we need a force where the speed is 40. So the force here will be K times 40, and this is squared. So what is F? So making F the subject and dividing the two equations, F will be equal to 40 squared divided by 20 squared times 800. And this is going to give us 40 squared divided by 20 squared times 800, which is 3200 newtons. That is the force corresponding to 40 meters per second. But we want the output power here. And we know that power is equal to force times velocity. Power is force times velocity. And if that is very true, so this is going to be equal to 3200 times the velocity there, which is 40. So this is times 40, which gives us 1000 or 12,008. Is it 12,000? It's 128,000 watts. So that means our answer is going to be 128 kilowatts. So the answer is going to be C. 128,000 is 128 kilowatts. Okay, an 8 Newton weight is attached to the lower end of a spring which is fixed at its upper end. The weight is initially held at rest at position X and the spring is unstretched. The weight is then released and falls to position Y, which is 4 centimeters below X. The weight oscillates and then eventually comes to rest at O, which is 2 centimeters below X. So this is what we are looking at. Initially, the weight is at position X. It is released and it goes to position Y. Then it oscillates and comes back to position O. So how much energy is lost from the system? How much energy is lost from the system? Okay, let's look at the position X here. Let's look at position X here. From X to Y, there is a change in gravitational potential energy. The change in gravitational potential energy here, which I will call E1, is going to be equal to mg times h, which will be equal to m, which mg is 8 newtons, so I'll say 8 newtons times h, which is going to be 0.4. Sorry, 0. I think 04 in meters. So that means the change in gravitational potential energy from X to Y is going to be equal to, I think that is 0.32 joules. 8 times 0.4, sorry, times 0.04, that is 0.32 joules. That is the change in gravitational potential energy from X to Y. And in this position here, there is, because the material has been stretched, it also, let's use this as the lowest point here. I'll use this position Y as the lowest point here. So if it has been stretched from X to Y and the change in gravitational potential energy is 0.32, it means the elastic potential energy here is going to be 0.32 joules. And that means the potential energy itself, or the gravitational potential energy, is going to be 0 if I'm using Y as the reference point, because the H will be 0. So it means the elastic potential energy here is going to be 0.32 and the gravitational potential energy at this level will be 0. That means at X, here gravitational potential energy will be therefore 0.32 joules. If it moves back from Y to X, the gravitational potential energy at point X will be 0.32 joules if point Y is the reference point. Okay, and now let's look at point O. Let's look at point O. So at point O, when it moves from Y to point O, so it is going to gain some gravitational potential energy. So the loss in gravitational, it is going to gain some gravitational potential energy, which is going to be, it will have moved through a distance from the reference point Y. It will have moved through a distance of 2 centimeters. So I'll simply say the gain in gravitational potential energy is equal to mgh, which is going to be the weight is it is mg times h. Mg is 8 newtons and h is going to be 0.02, which gives us 0.16 joules. So that is the gain gravitational potential energy when it moves from position Y to position O. So that means there is a loss. There is a loss. The total loss in gravitational potential energy from X to Y was 0.32 joules. The total loss was 0.32 joules. And we are seeing the gain in gravitational potential energy 0.16. There is some elastic potential energy here. The elastic potential energy in this position is also going to be a half times F times X, which is going to be a half. F is going to be the weight, which is 8, times X, which is X is going to be 0.02, because the extension there in comparison to position X is 0.02 or 2 centimeters. And I think this gives us, then that is let me check, 0.5 times 8 times 0.202. That gives us 0.08. So this is 0.08 in this position here. So the gain in gravitational potential energy is 0.16 and elastic potential energy is 0.08. So the total energy is going to be the sum of these two. So the sum is 0.08 plus 0.16, which gives us 0.24. So this is 0.24 joules. So that is going to be the total energy. But the question is asking for us to find how much energy is lost from the system. So note that initially, when it is displaced from X to Y, the energy is simply elastic potential energy, which is 0.32 joules. And when it comes to equilibrium at point, or when it comes to rest at point, or the total energy is 0.24 joules. Here it was 0.32 joules total energy because all the potential is taken to 0 and all remain with elastic potential energy. And here at position O, it is 0.24 joules. So now we want the loss. The loss is very simple. It will simply be 0.32 joules minus 0.24 joules. So this gives us 0.08 joules. So it means our answer is automatically going to be B. That question is quite technical, but the answer is going to be B. A bungee jumper on a platform over a river is attached to an elastic rope that is 20 meters long. When unstretched, he falls towards the river and his lowest point is 30 meters below the platform. The initial gravitational potential energy of the jumper is transferred to other forms during the jump. Which other forms of energy do the jumper and the rope have when the jumper has fallen halfway and when he is at the lowest point of his jump? So let's try to elaborate this with a simple diagram. Let's say this is the point where the rope is attached, and if the jumper is at the lowest point, if the jumper is to be at the lowest point, if the jumper is to be at the lowest point, then is supposed to be at 30 meters from this platform here. The lowest point is at 30 meters. That means halfway is going to be 15 meters. If the lowest point is at 30 meters, it means halfway of the lowest point is 15 meters. But remember the rope, the unstretched length of the rope is 10 meters. The unstretched length of the rope is 10 meters. So 10 meters could be around here. 20 meters could be just above. So this is 20 meters. For the unstretched length, it is 20 meters before it is stretched. Okay. So a bungee jumper on a platform over a river is attached to an elastic rope that is 20 meters long. So when he's halfway, the rope has not yet started stretching because the unstretched length of the rope is 20 meters. So when he's just 15 meters, downwards, it means the rope has not started stretching. For the rope to stretch, it must be 20 meters and above 20 meters below the platform. So it means when it's halfway, elastic potential energy is 0. So halfway, elastic potential energy is 0. Let's check. Which other forms of energy do the jumper and the rope have when the jumper has fallen halfway and when he is at the lowest point of his jump? So halfway elastic potential energy is not there. So that means we have eliminated the A and B. Halfway, we have seen why elastic potential energy is not there. The unstretched length is 20 meters, but halfway is 15 meters. That means the rope has not yet started stretching. And remember, the elastic potential energy is equal to half k x squared. So it depends on x. So if there is no x yet, there is no stretching, there is no extension of the rope yet, then there is no elastic potential energy. So we have eliminated A and B. Okay, but because he's moving, he has kinetic energy. And the lowest point, of course, here they have not mentioned gravitational potential energy. So we have to concentrate on kinetic energy and elastic potential energy. So let's now look at the lowest point. Of course, at the lowest point, there must be elastic potential energy because the rope must have stretched. At the lowest point, it is a distance of 30 meters, which is above the length of the rope. So it means the rope must have extended by 10 meters. So there must be elastic potential energy at the lowest point. But at the lowest point, it stops moving. It can't stretch any further. It can't move any further. At the lowest point, it stops moving. So kinetic energy becomes 0. So at the lowest point, V becomes 0. So it means kinetic energy becomes 0. But X is maximum. So it means elastic potential energy is also maximum. So it means our answer will be D. Halfway, there is kinetic energy only. Why? Because the rope has not yet started stretching. And at the lowest point, it stops moving, so kinetic energy goes to 0. But the extension is maximum, so the elastic potential energy is maximum. So there's elastic potential energy only at the lowest point. A cylinder contains a fixed mass of gas. The gas at a constant pressure of 1.3 times 10 power 5 pascals expands from a volume of 900 centimeters cubed to a volume of 1100 centimeters cubed. What is the work done by the gas during this expansion? What is the work done by the gas during this expansion? So work done is equal to pressure times the change in volume. So pressure is 1.3 times 10 power 5. The volume changes from 900 to 1100. So, but it is in centimeters cubed, so I will say times 10 power negative 6 to change it to meters cubed. So I have 1100 minus 900 times 1.3 exponent 5, which is 2.6. Sorry, that is 26,000. Is it 26,000? Okay, 1100 minus 900. Answer times 1 exponent negative 6 times 1.3 exponent 5. I think that is 26. So this is 26 joules. So the answer is going to be A. An object is thrown into air. It is thrown into air, so it means there is air resistance. Which graph shows how the gravitational potential energy EP of the object varies with height h? Gravitational potential energy. So gravitational potential energy is equal to mg h. So as the height h increases, if the mass of the object is constant, then it must, this one is showing that potential energy decreases because yet the object is thrown into air. This is showing when h increases, potential energy decreases. This one shows its potential energy increases to a maximum value, then it decreases as H increases, and has a limit, and yet this will not be, of course, true. This one is showing potential energy initially decreases, yet the height is increasing, so this is not going to be true. So the answer is automatically going to be A. Potential energy is directly proportional to H. When there is no H, then potential energy is zero, which helps us to eliminate B and D. And this graph was showing that the potential energy becomes maximum at a certain height, and then it starts decreasing as the height increases, and we don't see that in this formula here. So the answer is A. A car of mass 1,800 kilograms accelerates along a horizontal road so that its speed increases from 20 meters per second to 25 meters per second in a time of 5.4 seconds. What is the average useful power output of the car's engine? So power is going to be equal to work done divided by no, I want to use this one. So power is going to be, okay, let me say work done over time taken, and we see a change in kinetic energy. The work done will be equal to the change in kinetic energy over time taken. Change in kinetic energy will be a half times the mass, which is 1,800, times the change in V squared, which will be 25 squared minus 20 squared. That is the change in kinetic energy divided by time, which is 5.4 seconds. So 0.5 times 1,800 times 25 squared minus 20 squared divided by 5.4. So that is 37,500. So this is 37,500 watts. And I think this can round off to 38 kilowatts. So the answer is going to be B. A variable force is applied to ensure that a constant power is supplied to a train. Which graph best shows the variation? Which graph best shows the variation of the force F applied with the velocity V of the train? So we know that power is equal to force times velocity. So force is going to be equal to power over V. Remember, the power is constant, so that force is inversely proportional to V. So first of all, as V increases, F should be decreasing. As V increases, F should be decreasing. So it means B is wrong. As V increases, F should be decreasing. So C is wrong. As V increases, F should be decreasing. So D is wrong. These ones show different values. B shows that as V increases, F increases. C shows that as V increases, F increases until it tends to become constant with time. And D is showing that as V increases, F increases actually more rapidly. So it means the answer is automatically going to be A, asymptotic to both axes. Which statement about energy is not correct? Let's check. The first one, energy is never lost, but it may be transferred between different forms. That is true. It is in inelastic collision, total energy is constant. Total energy is constant. That is also true. It is just transformed from one form to another, but total energy is always constant. Then C, the efficiency of a system is the ratio of useful energy output, total energy input. That is correct. When a machine does work, friction reduces the total energy. This is not correct. Friction does not reduce total energy. It just wastes some of the energy, but the total energy remains the same. So the answer is going to be D. That is not correct. An electric kettle is rated as having an input of 1.5 kilowatts and an efficiency of 65%. The kettle is switched on for 2 minutes. How much energy is transferred to the water in the kettle? So we just use efficiency. Efficiency is equal to power output, useful power output over power input. Remember, power is energy over time, so this is going to be energy over T divided by the power input, which is 1.5 times 10 power 3. And we have to multiply this by, I don't need to multiply by 100, I'll just change it from percentage. So I will say efficiency is 0.65% is equal to the energy, which is E. Of course, the time is 2 minutes. 2 minutes is 2 times 60. Then we divide this by 1.5 times 10 power 3. So I'll check this. I'm making E the subject. So I'll say 0.65 times 1.5 exponent 3. Then I multiply this by 2 times 60. So this is giving me 117,000. So this is E is 117,000 joules. So this is 117 kilojoules, making the answer to be B. A girl of mass 50 kilograms runs up a flight of 20 steps in 7 seconds. Each step is 25 centimeters. What is the useful average output power? Useful average output power provided by the girl to climb the flight of steps. So power is simply going to be the work done over time taken. The work done will be the gain in gravitational potential energy. So this will be mgh over T. So I'll just substitute. So the power will be equal to, the mass is going to be 50 kilograms times G, which is 9.81. Then height, or the distance. We have 20 steps, each of 25 centimeters. So I'll say 20 times 25 times 10 power negative 2 to change the distance or the height into meters. Then divide by the time is 7 seconds. So this is over 7. So 50 times 9.81 times 20 times 25 exponent negative 2. So this is divided by 7. And I am getting 350. So this is 350 watts, which makes our answer to be precisely C. The total energy input in a process is partly transferred to useful energy output U, and partly transferred to energy that is waste, that is W. What is the efficiency? So efficiency is useful energy output, which is U, over total energy input, which is E in times 100. To change it to percentage, so our answer is automatically A. A gas is enclosed inside a cylinder which is fitted with a frictionless piston. Okay. Without wasting time, initially the gas has volume V1 and is in equilibrium with the external pressure P. The gas is then heated slowly so that it expands at a constant pressure, pushing the piston back until the volume of the gas increases to V2. So it means the change in volume is going to be V2 minus V1. How much work is done by the gas? So work done is equal to pressure times change in volume. So the work done will be the pressure P times the change in volume, which is V2 minus V1, which makes the answer to be automatically A. A car of mass 1,400 kilograms is traveling on a straight horizontal road at a constant speed of 25 meters per second. The output power from the car's engine is 30 kilowatts. The car then travels up a slope at 2 degrees to the horizontal, maintaining the same constant speed. It is maintaining the same constant speed. Okay. So what is the output power of the car's engine when traveling up the slope? What is the output power of the car's engine when traveling up the slope? First of all, let's find the driving force from the car. Let's find FD from the car. So we note that power is going to be equal to force times velocity. Power is going to be force times velocity. So the driving force, FD, Initially, the driving force is going to be the power was 30,000. Yes, 30,000 divided by V, which was 25. So this is going to be 1,200 newtons initially before reaching the slope. Now, when it is moving up the slope and it is maintaining the same constant velocity, it means the new driving force must be equal to this force it had in the horizontal plus the force it is going to use to overcome. Because initially the weight did not have any component down the slope, but now the weight, the mg here has a component down the slope, which is mg sine theta, if this is theta here. So it means there's a component down slope. There's a component of weight down the slope, which component is going to be the mg sine of that angle. And this is going to be the mass 1,400 times g, which is 9.81 sine of the angle, which is 2 degrees. Sine of the angle to 2 degrees. So that is the component of the weight down the slope. That means now the total force moving this car up the slope should cater for the force should be able to overcome the force, the component of the weight down the slope, and also move the car at the same speed as before. So the total weight is going to be the sum of the component of the weight plus the initial force which it had on the horizontal plane. So the new driving force, FD new, I'll call FD new, is going to be, what is this value by the way? 1,400 times 9.81 sine of 2. So that is 479.3. This was 479.3 newtons. So the new driving force is going to be 1,200 newtons plus 479.3 newtons. So that is going to be the total. Now the power this time from the engine must be able to maintain the speed and also overcome the component of the weight down the plane. So power is force times velocity. So this will be 1,200 plus 479.3, then times the velocity, which is 25. So what is the power here? I'll just say plus 1,200 times 25, which is 41,982. 41,982 watts, which means our answer is going to be 1, 2, 3. That is going to be 42 kilowatts. That will be 42 kilowatts, approximately 42 kilowatts. So our answer is going to be C. A man climbs slowly at a steady speed, that is a constant speed, to the top of a ladder. What is the main energy transfer taking place for the man as he climbs? The man climbs slowly at a steady speed, to the top of the ladder. Okay, so the man is using chemical energy. So there is chemical energy in the body, and that since the speed is constant speed, there is no change in what? In kinetic energy. So it is chemical energy potential, chemical potential to gravitational potential. Chemical to kinetic is wrong. Kinetic to gravitational potential is wrong because the steady speed. Thermal to the kinetic, there is no change in kinetic energy. So the answer is going to be A. Because of the constant speed, the change in kinetic energy is zero. So kinetic energy remains the same. During an interval of time, fuel supplies energy X to a car. Some of this energy is converted into kinetic energy as the car accelerates. The rest of the energy Y is lost as thermal energy. So that means total energy, which is input, is X. Fuel supplies energy X to the car. Some of this energy is converted. So total energy input is X. Then total useful energy output, because Y is wasted, so output is going to be X minus Y. So we know that efficiency is equal to the useful energy output, which will be X minus Y, divided by the energy input, which is X. So it means our answer is going to be C. A radar engine accelerates a train of total mass 800 tons, 1 ton is 1,000 kilograms, from rest to a speed of 50 meters per second. How much useful work must be done on the train to reach this speed? So we know that work done is equal to the change in kinetic energy. So work done is the change in kinetic energy. Remember, it starts from rest. So the work done is simply going to be a half times 800 times the final velocity is 50 squared, or you can say minus 0 squared to find the change in kinetic energy. So this is simply going to be 0.5 for a half times 800 times 50 squared. And this is giving us, this is giving me, oh, the mass was 800 tons. So I will say 800 times 1,000. So this will be a half times 800 times 1,000. Then I'll just say times 50 squared because the other one is 0. So I'll just say this times 1,000 is a 369. So that is 1.0 times 10 power 9. 1.0 times 10 power 9 joules. So the answer is going to be C. The mass is raised vertically in time t. The increase in its gravitational potential energy is EP, and the increase in its kinetic energy is EK. What is the average power input to the mass? What is the average power input to the mass? So the mass is raised vertically. In time t, the increase in its gravitational potential energy is EP, and the increase in its kinetic energy is EK. So we want the average power. So average power will be equal to the total energy divided by the time. So power is equal to energy, total energy over time. So this will be the potential energy plus the kinetic energy divided by T, which means our answer is going to be automatically D. Total energy or total work done divided by time. Water flows from a lake into a turbine. That is a vertical distance 9 meters below the lake as shown. The mass flow rate of the water is 2,400 kilograms per minute. So this is the same as 2,400 kilograms divided by 1 minute, which is 60 seconds. The turbine has an efficiency of 75%. What is the output power of the turbine? So efficiency, you know that efficiency, which is 0.75, is equal to the output power divided by the input power. Now the input power is the work done per unit time by the water which is coming from the height h. So power input is coming from the water, or the loss in gravitational potential energy. Power input is going to be loss in potential energy of the water per unit time, which is going to be m, mass of the water, times g times the height through which it falls over t. But we have mass per unit time, we just need to change it to seconds. So we shall simply say that the power output is going to be 0.75 times the power input, which is mg, which m is going to be 2,400 divided by 60 to change it to per second, kilograms per second, then times g, which is 9.81, then times h, which is going to be 90. 0.75 times 2,400 times 9.81 times 90 divided by 60. So this is giving us 26487. 26487. And this, when we change it to kilowatts, it becomes 26 kilowatts. So meaning that the answer is going to be A. A cyclist is traveling at a constant speed up a hill. The frictional force resisting the cyclist's motion is 8 newtons. The cyclist uses 450 joules of energy to travel a distance of 20 meters. What is the increase in gravitational potential energy of the cyclist? The increase in gravitational potential energy of the cyclist. The cyclist is traveling at a constant speed up a hill. What does this mean? This implies that the change in kinetic energy is zero because there is no change in speed. So what does that mean? The cyclist uses 450 joules of energy to travel a distance of 20 meters. That means all this energy does only two things: doing work against friction and giving the cyclist gravitational potential energy. So it means the 450 goes into gain in gravitational potential energy, gain in potential energy plus doing work against friction. I'll call W subscript F. So it means 450 is equal to the gain in gravitational potential energy plus the work done against friction, which is going to be frictional force times distance. So that will be 8 times distance, which is 20. Work done against friction is the frictional force times the distance. So this means the gain in potential energy is going to be equal to 450 minus 8 times 20, which gives us 290. So the answer here is going to be 290 joules, which makes it to be B. A stone of mass m falls from rest at the top of a cliff at a height h into the seabed, the sea below. Just before hitting the sea, the stone has speed v. Just before hitting the sea, the stone has speed v. What is the average force of air resistance acting on the stone during its fall? The average the average force of air resistance. Okay, so the stone is falling in air. Initially, remember the resultant force is equal to mass times acceleration. And if there is air resistance, the resultant force is the weight minus the force due to air resistance. Let me call it F air. So it means we have to find the acceleration first. So using the equations of motion, using one of the equations of motion, I will just use one of the equations of motion. That is v squared is equal to u squared plus 2as. I'm just looking for a here. So a is going to be equal to v squared. Because started from rest, u squared is going to be 0 divided by s will be h. So this will be equal to 2 times h. So I'm going to substitute for a with v squared over 2h. So the resultant force is mass times the acceleration, which is v squared over 2h. This will be equal to the weight, which is m times g. Then minus the force due to air resistance, which I'm going to call F air. So when I make F due to air resistance the subject, F due to air resistance is going to simply be equal to mg minus mv squared divided by 2h. So there's a common factor here of m. There's a common factor here of m. So this force is going to be m into g minus v squared over 2h. So that means our answer is going to be automatically C. Our answer is going to be C. A railway engine accelerates a train of total mass 1,200 tons. 1 ton is 1,000 kilograms from rest. Initial velocity is 0 to a speed of 75 meters per second. How much useful work must be done on the train to reach this speed? Useful work that must be done to reach that speed. So we know that work done is equal to the change in kinetic energy, or force times distance, but is the change in kinetic energy. So this will be a half times the mass. The mass is 1,200 times 1,000 times the change in its velocity. Because it starts from rest, so I'll simply say 75 squared minus 0 squared. So that is going to be the work done. I'm using the formula for kinetic energy, a half mv squared. So this means I have 0.5 for a half times 1200 times 1000, then times 75 squared. So this is giving me that is 3 billions. So this is 3.03375123123. Yes. Okay. So this is 36789. So that is 3.4. When I round off times 10 power 9 joules, which makes my answer to be C. What is a correct derivation of the equation relating power, force, and velocity? Derivation of the equation. Power is work done over time taken, which is true, and work done is force times displacement, which is true. So power will be force times displacement over time taken, which is true. So power will be force times velocity, which is true. So the answer is automatically A without wasting time. Power is work done over time taken, which is true, but work done is force times displacement or distance in the direction of the force. So that means B is not correct. That one, because distance over time taken is not velocity, it is speed. Then force over displacement is not velocity. Power is not force over velocity. Power is not force over velocity. So that one is wrong. The first column in the table gives 4 examples of work being done. The second column gives more detail of the action. Which row is not correct? Let's see the first one. A girl dives from a diving board into a swimming pool. That is the example. Work is done by the girl against the gravitational field. Is diving into a swimming pool. There is no work done by the girl against gravity. Work would be done by the girl if she was moving upwards, but she's diving downwards, so this one is not correct. A man pushes a car along a level road. Work is done by the man against friction. Yes, because he's pushing it, he's doing work against friction. That is correct. An electron is accelerated towards a positively charged plate. An electron is accelerated towards a positively charged plate. That is the example. Work is done on the electron by the electric field of the plate. Although we don't study electric field, when an electron moves towards a positive plate, then work is done on it. It loses energy because it is moving in the same direction as it would move if it was free to do so. But if it was moving against, then work would be done against the field. So the work would be done against the field. Towards work is done by the field. When work would be done against the field. A piston is pushed outwards as the gas expands. That is work done. Work is done on the on the atmosphere. That is very true. The gas is doing work on the atmosphere. Work is done on on the atmosphere by the gas. So that is also true. So A is not true. Work is done by the girl against the gravity, yet the girl is diving into a swimming pool. It's going in the same direction as the gravitational field. So that is not true. A steam turbine is used to drive a generator. The input power to the turbine is Pi and the output is P naught. The loss in the turbine, the power loss in the turbine is PL as shown. What is the efficiency? So efficiency is power output over power input. The output is P naught, the input is Pi. So that means our answer is simply D. Power output over power input. That is efficiency. A constant force pushes a block along a horizontal frictionless surface. The block moves from rest through a fixed distance. The block moves from rest through a fixed distance. What is the relationship between the final speed v of the block and its mass m? Okay, so let's use because the block moves from rest through a fixed distance, and we shall simply use v squared is equal to u squared plus 2as. So when u is 0, because the block starts from rest, so I'll simply say and u equals to 0. So it means v squared is equal to 2as. That means v squared is directly proportional to acceleration. V squared is directly proportional to acceleration, and we also know from force is equal to mass times acceleration. From force is equal to mass times acceleration, it means mass. It means okay. It means acceleration is equal to force over m, which means v squared, if this, because acceleration is inversely proportional to mass. Acceleration is inversely proportional to mass. It means that v squared is going to be inversely proportional to the mass. Since it is proportional to a and a is inversely proportional to m, it means v squared is inversely proportional to m. That means when I remove the square root, v is going to be inversely proportional to the square root of m, which means our answer is going to be C. So note how I started this from the equation of motion, and I set u to 0. So it means v squared was equal to 2as, and s was fixed. So 2s was a constant, so v squared was directly proportional to acceleration. But the force is equal to mass times acceleration, so acceleration is force over mass. So the acceleration is inversely proportional to the mass. Therefore, v squared must be inversely proportional to m. And when I remove the square root, I come up with that. A man has a mass of 80 kilograms. He ties himself to one end of a rope which passes over a single fixed pulley. He pulls on the other end of the rope to lift himself up at an average speed of 50 meters per second. What is the average useful power at which he is working? Okay, so we know that the power is work done over time taken, and work done is force times distance in the direction of the force, which gives us force times velocity. So he's going to try to overcome his weight. So the force is going to be m times g, then times the velocity. So this is going to be the mass, which is 80, times g, which is 9.81, then times v, which is 50, but remember it is in centimeters per second, so it is 50 times 10 power negative 2. Change it to meters per second. So we can now press our calculator. 80 times 9.81 times 50 exponent negative 2. That gives us 392.4. So this one is 392.4 watts. So when I move 3 steps, so when I divide by 1000 to get kilo, it becomes 0.3924 kilowatts. So the answer is going to be B. An iron is excited in a vacuum by a series of electrodes. A graph of the power supply to the iron is plotted against time. It is a graph of power against time. Of course, the area under this graph is going to be power times time. It will be somehow power times time, which must be energy. Power times time must be energy. Let's see the question. What is represented by the area under the graph between two values of t? The area under the graph between two values of t, since it will be multiplication of power times time, I think that is energy. So the average force on the iron, that is not true. The change in kinetic energy, most likely making sense. Momentum is not power times time. Change in velocity is not power times time. So it means our answer is going to be B. It must be relating to energy. Power times time is energy. So power times time is equal to energy. Even if there is a half or whatever you consider as a trapezium, there will be always a part which is power times time in the formula of the area that will be obtaining there. So that will be energy. Power is transferred through a machine as shown. So we see the power input we see the power output, we see the power loss. Automatically, this one is going to give us the answer as P naught for the efficiency. The efficiency is going to be P naught, that is the output power, useful output power over the total input power. A piston in a gas supply pump has an area of 400 centimeters squared. The pump moves the gas against fixed pressure of 300 pascals. During part of its stroke, the piston moves a distance 25 centimeters in one direction. How much work is done by the piston during this movement? So work done is equal to pressure times the change in volume. So this is very easy. Pressure is 3000. The volume is going to be the cross-sectional area times that length. So it is going to be 400 times the length, which is 25 distance. But this will be in centimeters cubed. So we multiply by 10 power negative 6 to change it to meters cubed. So 3000 times 400 times 25 exponent negative 6. That is 30. So the work done here is 30 joules. A turbine at a hydroelectric power station is situated 30 meters below the level of the surface of a large lake. The water passes through the turbine at a rate of 340 meters cubed per minute. The overall efficiency of the turbine and the generator system is 90% overall efficiency. What is the output power of the power station? The density of water is 1000 kilograms. We know efficiency is power output over power input, so the efficiency is 0.9. This should be equal to the power output over the power input. What is the power input? The power input would be total power input is going to be the work done in actually a turbine at a hydroelectric power station is situated 30 meters below the level of the surface of a large lake. So water must be pumped 30 meters. The water passes through the turbine at a rate of 340 meters cubed per minute. So we are going to find the work done, total work done by the water, and compare with the energy output or the power output. So the power input is going to be the work done by the water, which is per unit time, which is going to be the weight of the water, which is going to be mg times the distance it will move, mgh over t. But of course, we know the mass is density times volume. So this will be where there is mass, I'll put there density times volume, then times G times H over T. Okay, so I'll just substitute here, making power output the subject. Power out will be equal to 0.9 times power in, which power in will be the density, which is 1000 times volume over T. Volume over T, I'll just change it to per second. So it will be 340. Because it was per minute, I will divide this by 60 to change it to per second, times G, which is 9.81, times H, which is 30. So we shall just press our calculator. So 0.9 times 1000 times 340 times 9.81 times 30 divided by 60. So that is 1,500,000, 1,500,930. So these are another three, which is approximately 1.5 megawatts. So it means our answer is going to be B. Automatically, our answer is B. Car X is traveling at half the speed of car Y. Car X has twice the mass of car Y. Which statement is correct? So let's just use kinetic energy here. Let's start with car Y. let its mass be m and its speed be v. So it means kinetic energy of y is going to be a half times m times v squared. Let's look at x. Kinetic energy of x will be a half. Its mass is twice, so it will be twice m. And the speed is half, so it will be a half v squared. When you simplify this, you have a quarter v squared times m, so it becomes a quarter m v squared. You notice that when you multiply ex by 2, you get ey. So it means the kinetic energy of x is half that of y. So the answer is going to be A. Car x has half the kinetic energy of car y. So the answer is A. During refueling, a petrol car receives 50 liters of fuel in 90 seconds. The petrol has 34 megajoules of energy per liter. For every liter, the energy is 34 megajoules. For an electric car to receive the same amount of energy in the same time from 230-volt supply, what is the minimum current required? So note that power is equal to energy over time taken. And we want this power to also be equal to I times V. We want the power to be equal to I times V. So we want to find I. So let's just equate energy to IV, energy over time to IV. So the energy will be 34 mega is times 10 power 6. But that you remember was for just 1 liter, but it is supplied by 50 liters. So we shall say times 50. That will be total energy divided by time, which is 90 seconds. This should be equal to the current times V, which is equal to 230. So I'll just press my calculator, 34 exponent 6 times 50 divided by 90 divided by 230. So I am getting 8.2 times 10 power 1, 2, 3, 4. So current is equal to 8.2 times 10 power 4 amperes, which makes the answer to be B. A trolley rolls along a horizontal surface and then travels up a slope before reaching a second horizontal surface. The slope is of length L. The trolley has mass m. The slope is at an angle alpha to the horizontal surface. The second horizontal surface is at height h above the first surface. Assume negligible frictional forces. The acceleration of free fall is known. In order to determine the minimum initial velocity of the trolley for it to reach the top of the slope, which additional values are needed? So a trolley rolls along a horizontal surface and then travels up a slope before reaching a second horizontal surface. So here, since the frictional forces are negligible, there is no work done against friction. So it means the loss in kinetic energy along the horizontal surface at the bottom should be equal to the gain in potential energy when it reaches height h. So the loss in the loss in kinetic energy should be equal to the gain in potential energy. So the loss in kinetic energy is a half m u squared, which should be equal to the gain in potential energy, which is mgh. So m cancels. And if m cancels, and we want the minimum, in order to determine the minimum initial velocity of the trolley, when it reaches a height h, it comes to rest. So if in order to find u, we need only h. So we shall need h. So the answer is only h, or h only d. It is only h because g is known. So it is only h because u will be equal to twice gh under square root. And g is known, so it is only h. A man is running in a straight line. What is an approximate value of his kinetic energy? So let's approximate this to 1000 joules. Let's approximate that to be about 1000 joules. Remember, kinetic energy is a half m v squared. I've estimated this to be around 1000 joules. This is going to be a half. We are going to use this to predict the mass. Let's say a normal man is running in a straight line, perhaps is running at between 5 to 8 meters per second. Let me just say 5 squared. Because the person running fast, he runs at around 9, 10, 11, 12 meters per second. So I'll just take 5 squared because this one may not be in a race. So we have 1000 times 2 divided by 5 squared. That is 80 kilograms. So it means the mass is 80 kilograms. And this makes sense. This makes sense for a mass of a man to be 80 kilograms. If I use this one, I may get 800 kilograms, and doesn't make sense for a man to be 800 kilograms and is running. If I use 100 joules, I may get 80 kilograms. That cannot be a man. If I use 10, I may end up getting 0.8 kilograms, which cannot be a man. So it means the answer is C. The pump of a water pumping system uses 2 kilowatts of electrical power when raising water. The pumping system lifts 16 kilograms of water per second through a vertical height of 7 meters. What is the efficiency of the pumping system? We know that efficiency is power output, the useful power output over the total power input. So it is going to raise, the output is to raise water through a vertical distance of 7 meters. That should be the output. So that is going to be work done, which is gaining gravitational potential energy over time. Then divide by power input. The power input is 2 kilowatts, which is 2 times 10 power 3. So this is going to be M is 16, G is 9.81, and H is going to be 7. The time is 16 kilograms of water per second. So this is M over T is 16. Then divide by 2 times 10 power 3. Then we shall multiply this one by 100%. So this will be 16 times 9.81 times 7 divided by 2 exponent 3 times 100. So this gives us 55, approximately 55%. So that means the answer will be D. Some gas in a cylinder is supplied with thermal energy Q. The gas does useful work in expanding at constant pressure P from volume V naught to volume Vf. So that means the change in volume is going to be Vf minus V naught. So which expression gives the efficiency of this change? So efficiency, it means the work done here is going to be pressure times Vf minus V naught, because work done is pressure times change in volume. And this is going to be the work output. But the work input is given as some gas in a cylinder is supplied with thermal energy Q. So the energy input is Q. So efficiency is going to be the energy output, which is the work done, which is pressure into Vf minus V naught over the energy input, which is going to be equal to Q. So it means our answer is automatically going to be C for the efficiency. The power P required to move an object through a medium at constant speed depends on the speed V and the resistive force F acting on the object. The resistive force also depends on the speed V. Which row shows a possible relationship between speed V, resistive force F, and power? We know that power is equal to force times velocity. That one we know. And of course, we also know, or we have earlier on seen that from force equals to mass times acceleration, and acceleration equals to v squared minus u squared over 2s. If we consider initial velocity to be 0, we have also seen that the mass times acceleration is equal to the weight minus the frictional force, which means that mass, that is the mass, into v squared minus u squared over 2s is equal to w minus fr. If w is constant, u is 0, 2s and m are constants, it means v squared is directly proportional to the frictional force, or frictional force is directly proportional to v squared. So this is just a by the way. So frictional force is directly proportional to v squared. The frictional force or resistive force is directly proportional to v squared, but power is equal to F times V. So it means if I substitute for F, it means the power is going to be actually directly proportional to V cubed. If F is constant, the power is going to be directly proportional to V cubed, because if power is directly proportional to V and power is directly proportional to F, yet F is directly proportional to V squared, then power is directly proportional to V cubed. That is very true. So power must be directly proportional to V cubed. That makes our answer to be D. The frictional force is directly proportional to V squared. Power must be directly proportional to V cubed. So the answer is going to be D. Which amount of energy is not 2,400 joules? Let's check. These ones are easy to check. The decrease in gravitational potential energy of a body of mass 60 kilograms when it moves vertically downwards through 40 meters. So this is going to be mgh. Mass is 60, 9.81 times 40. That is not 2,400. It is already more than that. So this is not correct. The energy transferred in 15 seconds by a machine of power 160. So energy is equal to power times time, which is 160 times 15. I think that is 2,400. So this one is fine. The kinetic energy of a body of mass 12 kilograms moving at a speed of 20 meters per second. Kinetic energy is a half times mass times v. So that is 6 times 20 squared. That is 6 times 20 squared. I think that one is also correct. 0.5 times 12 times 20 squared. That one is correct. The work done by a gas expanding against a constant external pressure of 120 kilopascals. So work done is equal to pressure times change in volume. So that is 120,000 times 0.02, which is automatically 2,400. So this is also correct. So the wrong answer is A. It is not 2,400. Actually, it is the correct answer to this question, but it's not 2,400. A hammer of 10 joules of kinetic energy hits a nail and pushes it 5 millimeters into the plank. I think we have answered such a question. Both the hammer and the nail come to rest after the collision. What is the approximate average force that acts on the nail when it moves through 5 millimeters? Approximate force. So we shall just simply say that the change in kinetic energy is equal to the work done, which is simply equal to the force times the displacement. A hammer with 10 joules of kinetic energy, it finally comes to rest. So the change in kinetic energy is 10 joules, which will be equal to the average force times the distance, which is 5 times 10 power negative 3. And I think this is 2,000. So F is equal to 10 divided by 5 times 10 power negative 3, which is 2,000 newtons. The parachutist is falling at a constant velocity. At a constant velocity, that means there is no change in kinetic energy. Which statement is not correct? Not correct. Gravitational potential energy is converted into kinetic energy. There is no change in kinetic energy. Gravitational potential energy is gravitational potential energy is converted into kinetic energy of the air. Yes, for the air it is fine, not for the parachutist, that is fine. Gravitational potential energy is converted into kinetic energy of the parachutist. This statement is not correct. The parachutist is moving at constant velocity, so the change in his velocity is zero. And if there is no change in velocity, then the kinetic energy cannot change. So the gravitational potential energy is not converted into kinetic energy. So that is not true. So the answer is going to be B. Gravitational potential energy is converted into thermal energy of the air molecules. That one is fine. Gravitational potential energy is converted into thermal energy of the parachutists. That is fine, but not kinetic energy. The boy on a bicycle starts from rest and rolls down a hill inclined at 30 degrees to the horizontal. The boy and the bicycle have a combined mass of 25 kilograms. There is a frictional force of 30 newtons which is independent of the velocity of the bicycle. What is the kinetic energy of the boy? What is the kinetic energy of the boy and the bicycle after rolling 20 meters down the slope? Because it's rolling down the slope, we must be losing potential energy. So the loss in potential energy should be equal to work done against friction. There's work done against friction plus the change in kinetic energy or the gain in kinetic energy. So we want what is the kinetic energy of the boy and the bicycle after rolling? After rolling down the slope 20 meters. So because they start from rest, initial kinetic energy will be zero. So what I will be finding, change in kinetic energy will be just the final kinetic energy after 20 meters. So the loss in potential energy is going to be mgh. The work done against friction will be the frictional force times the distance in the direction of the force plus the change in just the final kinetic energy ek because the initial is zero. So ek is going to be m, where m is going to be 25 times g, which is 9.81, then times 25 times 9.81, then times h, which is going to be 10 because h is going to be 10, I think, because sine of that is half. So this is 30, this is 30 degrees, and this distance is given as 20 meters. So I want h, that is h. So sine of 30 is equal to h over 20. So h is going to be sine 30 times 2. So this is going to be 20 sine of 30. That is the distance. I mean, that is the vertical height. So that is mgh minus f, frictional force, which is 30 times the distance. Of course, for friction, we shall consider 20 meters, so times 20. So I just subtract this. 25 times 9.81 times 20 sine of 30, then minus 600, which gives us 1852 or 1853 joules, which makes the answer to be A, 1850 joules. An escalator in an underground station has 250 people standing on it and is moving with a velocity of 4.3 meters per second. The average mass of a person is 78 kilograms and the angle of the escalator to the horizontal is 40 degrees. What is the minimum power required to lift these people? Minimum power required to lift these people. So we note that power is going to be force times velocity, but remember there's an angle and it is moving with a velocity of 4.3. So we can assume that the velocity is constant, so the resultant force is zero. The component of the weight down the slope is equal to the driving force. So power is simply going to be the force times velocity. And the force upwards is going to be the same as the force downwards because it's moving with a constant velocity of 4.3. So this will be mg sine. This will be mg sine of 40 then times v. So m is 78 kilograms for one person, but they are 250, so times 250, that is the total mass, times 9.81 to get the weight, then sine of 40 because it is inclined at 40 degrees, so that is the total force, then times v, which is 4.3. So I'll just press my calculator, 78 times 250 times 9.81 sine of 40, then times 4.3. So this is giving me 528,736 or 37. 528,737 watts. In a kilo, this is 1, 2, 3, 1, 2. So in a kilo, when I remove those three, when I divide by 1000 is 528.7 kilowatts or 530 kilowatts. So the answer is going to be C. An electric motor operating a lift has an output of 20 kilowatts. The lift and passengers have a combined mass of 1,500 kilograms. The motor raises the lift through a distance of 20 meters. How long does it take? How long does it take? So they have told us the power output is 20 kilowatts. And we know that power is equal to work done over time taken. And the work done will be equal to mg. So this will be mg times h because it is doing work against gravity. So the work done is mg times h. Then this is going to be divided by time. So the power is given as 20 times 10 power 3. This is equal to m, which is 1,500 times g, which is 9.81 times h. H is 20 meters. Then divide by t. I'll just make t the subject in my calculator. 1,500 times 9.81 times 20 divide by the power, which is 20 exponent 3, which is 14.7, which is approximately 15. So this is going to be 15 seconds, that is B. An object of mass 0.3 kilograms is thrown vertically upwards from the ground with an initial velocity of 80 meters per second. The object reaches a maximum height of 1.9. That, of course, at maximum height V is 0. How much work is done against air resistance as the object raises to its maximum height? How much work is done against air resistance as the object raises to its maximum height? Okay, so when it is raising to its maximum height, one, it is losing kinetic energy, so loss in kinetic energy. Two, it is gaining potential energy, should be equal to the gain in potential energy. And three, there is work done against friction, so plus work done against friction. So how much work is done against friction? So I'll just substitute. So the work done against friction is going to be the loss in kinetic energy, which is a half times the mass, 0.3 times V. Of course, initially finally it is going to be 0, but initially it is going to be due to 8 meters per second, so that is 8 squared, minus the gain in potential energy, which is mgh. The kinetic energy is a half mv squared, and the potential energy is mgh. So minus m, which is 0.3, times g, which is 9.81, times h, which is 1.9. So I'll just check this on my calculator for work done. A half is 0.5 times 0.3 times 8 squared minus, open brackets, 0.3 times 9.81 times 1.9. So this is giving me 4.0083. That means the work done is 4.0 joules. So the answer is going to be A. A racing car has an output power of 300 kilowatts. When traveling at a constant speed of 60 meters per second, what's the total resistive force acting on the car? Because the speed is constant, it means the forward force is equal to the backward, the opposing force. So I'll simply say that power is equal to force times velocity. So 300,000 is equal to the frictional force times the velocity, which is 60. So I'll just say 300,000 divided by 60, which is 5,000. So F is equal to 5,000 newtons. So that means our answer is going to be 5 kilonewtons. So the answer is going to be A. The diagram shows the design of a water wheel which drives a generator to produce electrical power. The flow rate of the water is 200 kilograms per second. The generator supplies a current of 32 amperes at a voltage of 230 volts. Ignoring any changes in the kinetic energy of the water, what is the efficiency of the system? So remember, efficiency is equal to the power output divided by the power input. So the power output, because the generator supplies a current of 32 amperes at a voltage of 230 volts, so the power output is going to be I times V. But then the power input must be driving a generator to produce. The diagram shows the design of a water wheel. Now, which drives a generator to produce electrical energy. So the work done in driving a generator. The flow rate of the water is 200 kilograms per second. So we must look at the flow rate of this water. So the power input is going to be the work done in moving this water, which is going to be mgh divided by t. So we shall now just substitute here. So I is 32 times v, which is 230, divided by m over t is given as 200, times g, which is 9.81. Since they told us, we are seeing that the water is moved through a height of 80 meters, so the h is going to be 80 meters. So I'll just press my calculator and maybe times 100 to make it a percentage. So this is going to be 32 times 30 divided by 200 times 9.81 times 8, then times 100, which is 6.1%. So this is 6.1%. 6.1%. Let me check it again. 32 times 230 divided by, open brackets, 200 times 9.81 times 8. Then times 100. I think that is around 46.89, which is 47, not 6.1. So that is pressed my calculator wrongly. So that is approximately 47%. So the answer is going to be D. A hydroelectric power station uses the gravitational potential energy of water to generate electrical energy. In one particular power station, the mass of water flowing per unit time is 1.5 times 10 power 5 kilograms per second. The water falls through a height of 120 meters. So the work done is going to be power will be mgh over t. The electrical power generated is 100 megawatts. So that is the power output. What is the efficiency of the power station? So efficiency is going to be the power output, which is 100 times 10 power 6 watts, over power input. the power input is going to be the work done over time, which is going to be mgh over t. So m over t is 1.5 times 10 power 5, then g is 9.81 times t, which t is, of course, t as m over t is 1.5 times 10 power 5, g is 9.81, and h is 120. H is 120. So this is 100 exponent 6 divided by 9.81 times 120 times 1.5 exponent 5. So that gives us 0. I will just multiply this by 100 because they are expressed as percentages times 100, which is approximately 57%. So the answer is going to be 57%, which makes it to be C. An engine transforms thermal energy into mechanical work. An engine transforms mechanical energy into, thermal energy into mechanical work. The engine takes in thermal energy Q in, so this is the energy input from a heat source, and gives out thermal energy Q out to a heat sink, so this is what is wasted, producing useful work W. What is the efficiency? So efficiency is useful work output, which is W, over total energy input, which is Q in. So that means the answer is automatically C. A truck of mass 500 kilograms moves from rest at the top of a section of a truck 400 meters long and 30 meters high. So this is a truck, which is a vehicle, and the other is a truck, which is a road, as shown. The frictional force acting on the truck is 250 newtons throughout its journey. Frictional force is 250 newtons throughout its journey. What is the final speed of the truck? So as it loses potential energy, it is gaining kinetic energy and doing work against friction. So we shall simply say the loss in potential energy is going to be equal to the gain in kinetic energy, is going to be equal to the gain in kinetic energy plus the work done against friction. So the question is, what is the final speed of the truck? So the loss in gravitational potential energy is mgh. Remember, potential energy is mgh. Then kinetic energy is a half mv squared. And then the work done is going to be the frictional force times the distance in the direction of the force. But they had given us the frictional force, and the distance is 400 meters. So we shall just substitute mgh, which is 500 times 9.81 times h, which is 30, should be equal to the kinetic energy. It starts from rest. Initial kinetic energy is 0, so I'll simply say a half times mass, which is 500, then times v squared, which is going to be the final speed, v squared. The other one is minus 0 squared, then plus the work done, which is the frictional force, that is 250, times the distance, which is 400. Of course, for frictional force, I have to get the distance along the track. So let's find V by simply pressing the calculator. 500 times 9.81 times 30 minus 250 times 400. Then I'll multiply this by 2, divide by 500. So I find the square root. Root of the answer, which is 13.7, which is approximately 4. So V is going to be 14 meters per second. So it means our answer is going to be A. Which condition must apply for the work done by an expanding gas to be pressure times change in volume, where P is the pressure of the gas and delta V is work done by, and delta V is its change in volume? Which condition must be satisfied? So A, no thermal energy must be supplied to the gas. The expansion must be at a constant rate. The pressure must be constant. So the answer is C, the pressure should be constant. So if the pressure is constant, whether there is thermal energy supplied or not, as long as there is a change in volume, then it means there is work done by an expanding gas. So the pressure must be constant. On the surface of a planet, 30 joules of work is done against gravity to raise 1 kilogram through a height of 1 meter. So let's check. We know that work done is equal to force times the distance in the direction of the force, or times displacement. So we are saying 30 joules are done. So 30 joules will be equal to, the force will be mg, then times the distance, or times the height, mgh. Let me just say mgh. So we have that 30 is equal to the mass, which is 1, times g, which is not known, times h, which is 10. So g is going to be 3 meters, 3 kilograms. G on that planet is going to be 3 newtons. I'll just say 3 meters per second squared. So G will be, so this is 1.0 times G times 10. So G will be equal to 3 meters per second. That is the acceleration of free fall on that planet. How much work must be done to raise a mass of 4 kilograms through a height of 5 meters? So G is going to be the same. So work done is equal to the mass, which is 4, times G, which is 3, times the height, which is 5. So 4 times 3 times 5, that is 12 times 5, which I think is 60. So this is 60 joules. So the answer is going to be B. I just use the first conditions to find G, which is going to be the same for the second mass. So the answer is going to be B. The speed of a car increases from 10 meters per second to 15 meters per second, and its kinetic energy increases by E1. Later, the speed of the car increases from 15 meters per second to 25 meters per second, and its kinetic energy increases by E2. What is the ratio? E2 over E1. That is very easy. E2 over E1 is going to be, for E2, which is a half, times the mass. The speed changes from 15 to 20, so I'll say 25 squared minus 15 squared, divide by, for E1, it is a half. The same mass, the speed changes from 10 to 15, so I'll say 15 squared minus 10 squared. So a half m has cancelled. So I have that 25 squared minus 15 squared. That is 400, divided by 15 squared minus 10 squared, which is 125. So we can divide 400 by 125, which gives us 3.2. So this is 3.2, which makes the answer to be C. A car travels at a constant speed of 25 meters per second up a slope. The speed is constant. There is no change in kinetic energy. Resultant force is 0. The wheels driven by the engine exert a forward force of 300 newtons. There is a dragger force due to air resistance and friction of 2,100 newtons. The weight of the car has a component down the slope of 900 newtons. What's the rate at which thermal energy is dissipated? So here we just look for the forces which dissipate energy, and that is basically friction. Only friction, only the 2,100 newtons will dissipate energy in form of heat. So it means the rate at which thermal energy is dissipated, which is power, is force times velocity. So we shall just take the friction force, which is 2,100 times the speed, which is 25. It is the friction only which will of the dragger force or the air resistance and the friction, which will dissipate energy in the form of heat. So here we just press our calculator, 2100 times 25, and that is 52500 watts, which is the same as 5.3 times 10 power 4 watts. So the answer is automatically C. A team of 9 dogs can pull a sledge with a combined force of 800 newtons. It is a team of 9 dogs at a speed of 1.5 meters per second for 360 minutes. What is the average work done by each dog? That is for one dog. What is the average work done by each dog during this time? Okay, let's find the total work. Of course, I'll just divide the total work done by 9. So total work done is equal to force times distance in the direction of the force. Total work done will be force times distance in the direction of the force. And of course, the distance will be equal to the speed times the time. So this will be equal to the force, which is 800 newtons, times the speed, which is 1.5, times the time, which is 360 minutes. We multiply it by 60 to change it to seconds. That's total work done, but we want work done by each dog, so I will divide this by 9. So the work done will be 800 times 1.5 times 360 times 60 divided by 9. So each dog is going to be doing 2880. So that is 288000. There are 4 zeros. Joules of work, which is approximately, these are 4, 5, 6, so that is 2.9 times 10 power 6 joules. So the answer will be C. Which statement is correct? The ball lands on the ground and bounces. The kinetic energy changes sign because the ball changes direction. Kinetic energy is a scalar quantity, so this statement is not correct. A car drives up a slope at a steady speed. Steady speed means constant velocity. The power generated by the car equals potential energy gained per unit time. The power is equal to the potential energy per unit time. A car drives up a slope at a steady speed, that is at a constant speed. The power gained by the engine equals the potential energy gained per unit time. I think that will not make any good sense. An electric heater can be 100% efficient. That is very true. An electric heater is designed to heat actually. So if it converts all the energy to heat, then it can be 100% efficient because it is designed, the output is heat. So the heat coming from the heater is not a waste, it is actually the output. That is very correct. It is impossible for momentum to be conserved in a collision. That is not true. Momentum is always conserved for an isolated system of interacting bodies. So the answer is C. The diagram shows a pump called a hydraulic ram. There is a large reservoir lake, long inclined approach pipe. There is a pump, there is a lift height, and a small high tank to be filled. In one such pump, the long approach pipe holds 500 kilograms of water. A valve shuts when the speed of this water reaches 2 meters per second, and the kinetic energy of the water is used to lift a small quantity of water by a height of 15 meters. The efficiency of the pump is 10%. Which mass of water could be lifted 15 meters high? Okay, so we have the input energy is kinetic energy of the water. So kinetic energy, or let's say efficiency, is going to be equal to the energy output, which is going to be potential energy. in raising the water to that height over the energy input, which is going to actually be kinetic energy. So this is going to be mgh divided by the kinetic energy, which is a half mv squared. So that is going to be the efficiency. That is going to be the efficiency, but the efficiency has been given as 10, which is 0.1. So 0.1 is equal to m. Oh, so these m's are not the same. This is m for the water which is being raised. Let me call it m2. And this is m1 for the water which is held in the pipe, in the long approach pipe, which I'm calling m1. So this is going to be 0.1 is equal to m2, the water which is lifted up, times g, which is 9.81. It is lifted through a height of 15, so I will say times 15, divided by a half the mass of the water which is held in the approach pipe, the long approach pipe, which is 500, times the speed it reaches, which is 2, but this is squared. So I'll just press my calculator here and make m the subject. So I have 0.1 times 0.5 for a half times 500 times 2 squared. Then I divide this by 9.81 times 15. And V is going to, M2 is going to be 0.68. So M2, which is the mass raised, is 0.68 kilograms, which makes the answer to be B. A conveyor belt is driven at a velocity v by a motor. Sand drops vertically onto the belt at a rate of m kilograms per second. Okay. What is the additional power needed to keep the conveyor belt moving at a steady speed when the sand starts to fall on it? So I want you to note, first of all, that power is equal to force times velocity. But remember, force is equal to the rate of change of momentum. Force is equal to the rate of change of momentum. And also I want you to note that momentum, don't confuse P for momentum and P for power this time. And we also know that momentum is equal to the mass times velocity. So momentum is equal to mass times velocity. And the rate of change of momentum, the rate of change of momentum, I'll just use MTM for momentum, can be written as change. Let me use straight power in full. So the rate of change of momentum is going to be delta P over T, which is the same as, because what is changing, I think, is the mass. The mass is the one changing. Sand drops vertically onto the belt at a rate of m kilograms per second. So I'll say the change in mass over time times the velocity. That is the rate of change of momentum. And the rate of change of mass over time is given as small m. So this is going to be m, then times the velocity v. So that is the rate of change of momentum. It is mass times velocity. But remember, small m is mass, is the rate at which it is mass per unit time. Small m is mass per unit time because it's in kilograms per second. That's why you have change in mass over time is small m. Okay. So since force is, since the rate of change of momentum is force, so it means force is going to be m times v. And remember, power is force times velocity. So power will be equal to force, which is mv again times v. So which means the power is going to be mv squared. So note very carefully, power is force times velocity, but force is the rate of change of momentum. And momentum is mass times velocity. So the rate of change of momentum is the change in mass over time, then times the velocity. which means it gives us simply m times v, that is the force. But power is force times velocity, so that means our answer is automatically going to be D. A uniform solid block has weight 500 newtons, width 0.4 meters, and height 0.6 meters. The block rests on the edge of a step of depth 0.80 meters, as shown. The block is knocked over the edge of the step and rotates through 90 degrees before coming to rest with the 0.6 meters edge horizontal. So this horizontal distance here is 0.6 meters. It is not flipped, it is just pushed. It is knocked over so that it just falls like this. Assuming here it is now falling. It just falls and then it goes down. It is knocked over and it falls through 90 degrees. The diagram shows a hydroelectric, what is the change in gravitational potential energy of the block? So to find potential energy, we shall use the height of the height as the reference point, the height as the reference point. The center of gravity as a reference point. So initially the center of gravity is, when it is here, it is at a distance of, this distance is 0 point, I'll rub off this part here. Initially this distance is 0.3 meters. But when it has fallen to this level here, the center of gravity, this distance, or the distance from the base, is going to be 0.2 meters. So this is also 0.2 meters. Remember, from this level here to the base is 0.8 minus 0.4, which makes this distance to be 0.4 meters. So the total change in height is going to be equal to 0.3 plus 0.4 plus 0.2, which is equal to 0.9 meters. So the center of gravity, the horizontal line, the center of gravity, that is at the midpoint, the center of gravity changes through a vertical height of 0.9 meters. Therefore, the change in gravitational potential energy is going to be mg times the change in the height h. So mg is going to be 500 newtons, then times the change in height, which is 0.9. So this gives us 500 times 0.9, which is 450 joules. So that is 450 joules. So it means our answer is going to be C. What is the change in gravitational potential energy of the block? So the answer is going to be C automatically. Just notice how I got the heights. I just looked at the center of gravity. It is at the midpoint. If the object is uniform, like they say, it is a uniform solid block. So its center of gravity is at the midpoint. That's why I said its center of gravity was initially at a height of 0.3 meters from this platform here. And the center of gravity now is going to be, because it has flipped, the center of gravity is at a height of 0.4 meters from this platform here. So the change in the position of the center of gravity was 0.9 meters. Okay, lastly for part 3, the diagram shows a hydroelectric power station. The reservoir is linked to the turbines by a pipe of uniform cross-section area. Water flows from X to Y at constant speed. Which statement about the change of energy of the water as it moves from X to Y is correct? Which statement about the change of energy of the water as it moves from X to Y is correct? Okay, of course, as it moves from X to Y, the height is decreasing, so it must be losing gravitational potential energy. So where we see it gains gravitational potential energy, that is wrong. It loses both elastic potential energy. There is no elastic potential energy here. It loses both elastic potential energy. I say there is no elastic potential energy. Let me see. Water flows from X to Y at a constant speed. Which statement about the change of energy of the water as it moves from X to Y is correct. The diagram shows a hydroelectric power station. The reservoir is linked to the tubes by a pipe of uniform cross-sectional area. Okay, so it gains both gravitational. I said here it is not gaining gravitational potential energy because the height is decreasing. It loses both elastic potential energy and kinetic energy. Because it is flowing, it is gaining kinetic energy. So this is wrong. It loses both elastic potential energy and gravitational potential energy. Of course, it is not. It is losing gravitational potential energy, but can't be losing elastic potential energy. It loses gravitational potential energy, which is true because of the change in height, and is going to gain elastic potential energy. So it is going to gain elastic potential energy. That means our answer is going to be most likely D, because the rest are not making good sense at all. Although it is confusing when it comes to how the water gains elastic potential energy, but the only answer which is making sense is D. Okay, so finally, let's stop there in part 3, and we shall meet in part 4. We have stopped on page 40. I think we have stopped on page 46. We shall start from page 47 in part 4. See you and bye bye. For any errors, you can always let me know. I am bound to make such errors, and sorry for that in advance. Bye bye.